Welcome to session 8 on machine learning. We have 4 papers. The first paper is titled "A Two-Phases Exact Algorithm for Optimization of Neural Network Ensemble," and the speaker will be Keliang Wang. Please, can you pass the video?
Hi everyone, this is Keliang. Today I'm going to present our paper, a two-stage exact algorithm for optimization of neural network ensemble. This is a joint work with professors Leonardo Lozano, David Bergman, and Carlos Cardonha. In this first section, I'd like to use 2 applications to introduce the motivation on why we want to optimize the neural network. This is our interested optimization model, where the object function is a trained neural network with the input X. This X input to the neural network is also the decision variables of this optimization model. In other words, solving this model will find us a X star that maximize or minimize the output of this neural network. Consider that we have data set of a red wine quality score where the inputs are some controllable parameters in production that will affect the quality of red wine, such as fixed acidity, residual sugar, and pH value, and so on. The output is the quality score. We can train a neural network on the historical data sets and then embed the trained neural network to this model. Solving this model will give us a X star that will maximize the quality score measured by this neural network. If we have a good approximation of the underlying mapping, and hopefully in real production, using the setting of this X star will generate a high quality red wine. Another application is on global optimization problem. Suppose we can sample some data points from this benchmark function f. By training a neural network to approximate this f of x, if we then embed the trained neural network in x to the optimization model, by solving this model will hopefully get us a X star that is the close to the true global minimum when evaluated using F. Many of the applications where this optimization model fit in rely on the remarkable predictive performance of the neural network. In machine learning field, there is an even more powerful technique that could bring the performance of neural network to another level. That is the ensemble learning. Ensemble method combines predictions of multiple estimators to improve the predictive performance over a single estimator. Neural network ensemble also receives a lot of attention. It consists of a committee of neural networks, and it's been proved that the neural network ensemble provides lower generalization error than a single estimator. Among many ensemble techniques in this paper, we focus on using backing ensemble. There are a number of neural networks in this committee, and the final output is the average of the outputs of all neural networks in the ensemble. Hence, by incorporating the neural network ensemble into the optimization problem, our focal optimization model becomes this. This slide is some literature review. One line of relevant literature is on using neural network as a surrogate. In the first paper, the authors study how to allocate the workloads for a multi-core system in a chip so as to minimize the working temperature of the chip. It uses a neural network to approximate the system thermal behavior. In the second paper, the authors studied several deterministic global optimization problems with single neural network embedded. Their algorithm rely on the algorithmic relaxation of the nonlinear activation function of the neural network. These two works use different formulation techniques as ours. What's more relevant to our model formulation is on the interplay between mixed integer programming and the ReLU neural network. The paper by Viscati et al. Was one of the first to formulate the ReLU neural network into a mixed integer programming. In their paper, they also propose a progressive bound titling to speed up this optimization. Recently, in the deep learning field, many recent works are using mixed integer programming to study the properties of the neural network, such as the output range analysis and the robustness verification. To the best of our knowledge, there is no study on integrating the neural network ensemble into the optimization model. Before talking about the detailed MIP formulation, in this section, we compare the performance of a single neural network with the neural network ensemble. We have two global optimization problems here, and both of their independent variables are in a box domain, and we know its actual global minimum. So first, 1,000 data points are sampled from these two functions using Latin hypercube sampling. We train single neural network and also the neural network ensembles. For the training, we did a comprehensive hyperparameter tuning. And then we choose estimators with the best cross-validation score to embed into the optimization problem. And then after solving the optimization problem, we evaluate the optimal solution and compare that the evaluation to the true global minimum. In this slide shows the 95% confidence interval of the evaluation of the optimal solutions. Each confidence interval corresponds to an estimator. The blue represents a single neural network and the orange represents a neural network ensemble. The x-axis shows the average R2 score on test set for each estimator. Note that finding the exact global minimum is not our purpose in this context. It's more important to show the relative performance of a single neural network versus a ensemble. From these two plots, the ensemble generates a more stable solutions and also closer to the true global minimum, which gives us a test of advantage of integrating the ensemble into the optimization model. In this section is about the formulation. We consider neural network having multi-layer perception structure. Here it shows the calculation at a single neuron. It receives the outputs from the previous layer and then first do an alpha combination using weights and biases. After that, it applies an activation function. In this paper, we consider the ReLU activation function because first, it can be exactly encoded into a MIP, and the second, ReLU activation is the top choice when people do neural network training. A neuron is located by this triple where I is the index of neural network, L is the layers index, J is the positions of the neuron in this layer. This is our basic model formulation. We denote it as the ENN. The objective is the average output of all neural networks. 2b ensures that let the decision variable x be the inputs to the neural network and ensures that all neural networks share the same input x. H is the pre-value value, and 2c ensures that the output of the neural network only calculate the pre-value value without applying any activation function. Y here is the post-value value. The binary variable z is used to indicate if this pre-value h is non-negative or not, meaning the neuron is activated or deactivated. This implication is implied by it's connected through the big M constraint. For convenience, we will denote the space defined by constraint 2c to 2h as psi. We can do a reformulation of the basic model ENN by adding E number of copies of inputs. And then if we remove this constraint 3b, we can observe that our relaxation display a block diagonal structure that allows us to decompose it into some simpler problems, which is the relaxed ENN I for each neural network I, where the psi I is the subspace of the psi we just defined. Based on the above analysis, we have the following two-stage optimization algorithm. In the first stage, we solve relaxation RENN for each neural network and obtain the optimal value U of I. In the second stage, we solve a strengthened version of ENN by adding the bound constraints. This is a simple yet effective algorithm, which we will see in the next section. We compare the two-stage algorithm with the basic model formulation ENN on solving ensemble-based model. We choose two problems. One is Pick's function we've just seen. The other is a real-world dataset that is used to study the compressive strength of concrete. It has 8 input features. We're going to train different ensemble configurations for the optimization, and each ensemble is characterized by the optimization difficulty. That is the number of neural networks and also the topology of each neural network in the ensemble. So for each configuration, we did 5 replications and the average the results. So there are 200 instances for each problem. This slide shows the solution time comparison between two methods. On the x-axis is the execution time of the two-stage algorithm. The y-axis is the execution time of the basic model formulation ENN. Each dot represents an ensemble configuration specified by the color and the size of the dot. Based on these two plots, we can see that two-stage algorithm outperforms the ENN formulation in almost all cases for both problems. These two plots show the cumulative frequency distribution combining the execution time and the arithmetic gap. The figures show that two-stage algorithm solves more instances than ENN after any amount of time with much smaller gaps at the time limit. The advantage of two-stage algorithm is even more highlighted in the concrete problem, where all instances are solved to optimality within 300 seconds. To summarize, in this short paper, we provide a first probe into integrating neural network ensemble as part of an optimization problem. We also present a two-stage algorithm that outperforms the basic formulation. Using mixed integer programming to study neural network is a fast-growing field in recent years. Some future directions are we can deploy some pre-processing techniques. We can also study some more advanced techniques to further speed up the optimization. This slide shows some reference we mentioned in this presentation. Thank you for listening. I'm happy to take any questions.
So curious.
Okay, thank you very much. Are there any questions?
Close the field. Sorry.
I can. Okay, it doesn't. There aren't any questions. I have a question. So you mentioned the mixed integer linear programming model of Fischetti and all, but the model that you use is different. So the question is, could you have used the model of Fischetti and all?
Yeah, we are using the big M formulation in our mixed integer programming model that is currently mostly used in the recent literature, how to formulate a ReLU neural network. And that is our basic model formulation. And our two-stage algorithm, we just improve that basic model formulation on solving this optimization problem.
Okay. The question was whether the basic model of Fischetti and Joao could be competitive or not. I'm not saying it's competitive. I don't know. I was just wondering if it could be competitive. So that was one of the questions. The other question, the other question was, I'm not sure if I understood how many neurons are you analyzing for each run. How many neurons do you have in your neural network ensemble?
So, yeah, we tested the sample size range from the 2 to 10 neural networks in the ensemble, and each neural network consists of the Wang hidden layers, with the neurons in the hidden layer range from 20 to 200. Yeah.
Okay. Are there any more questions regarding this talk? Okay, I have another question, which it was not clear to me. So you say that you're sampling 1,000 data points.
Yes.
Yeah. Why 1,000? Is that a sufficient number? Do you know? Yeah. Just where? How did you get to 1,000? The number of 1,000.
I think we used 1,000 data points, and we did a comparison. We did hybrid tuning over this 1,000 data points. So we then pick the best performance estimators to embed into the optimization model. And when we improve the data points like to 5,000, the test MSE remains basically the same. So it doesn't affect the predictive performance of the machine learning model of the neural network.
Okay. Thank you very much. Are there any? We have time for one quick question. If there is any more questions. If there aren't, I would like to thank the speaker for the very nice talk and answering the questions.